Hi, I'm Jacob Cebulski. In this presentation, I'm going to discuss the project conducted jointly with Tan Nguyen from the School of IT, Deakin University, Australia, and he's from the Institute of Research and Development, Dai Tan University, Vietnam. We're going to present a project which we published in Quantum Information Processing in December 2023, and the focus is on strategies for dealing with barren plateaus in training quantum machine learning models. In that project, we are looking at certain type of quantum machine learning models. They are variation quantum models, and they're being processed with variation quantum algorithm. Such models have usually a feature map which encodes the input data, has an ansatz, a circuit with trainable parameters responsible for processing of quantum information, and a measurement which is interpreting the quantum states of the circuit. When it comes to the process, it's a hybrid process where we rely on the classical optimizer manipulating the parameters of the ansatz, which could be then run on the quantum machine, and the results could be subjected to the cost function, and it's being fed iteratively into the optimizer until the process converges at some optimum point. This process can be affected by barren plateaus. They are large, flat areas in a quantum model cost landscape, which usually affect negatively the model optimization process. The phenomenon is related to the problem of vanishing gradients in classical neural networks, and it has many causes. One is the structure and the size of the ansatz. The second is the initialization of the ansatz parameters and the nature of the cost function, and finally other factors such as the data, the optimizer, the quantum machine noise, and so on. The true nature of barren plateaus is commonly idealized and in consequence is often misunderstood. Here is a typical cost landscape of a very simple quantum model which had 114 parameters, and the parameter space is large, 114 dimensional, but it's not as large as in other real life models. If we want to visualize it, we could project it into the first and second principal components, and in this way we could actually see the optimization path, the red line here, the optimum point, and possibly some plateau, and that plateau is not always nice and flat and smooth. It could be initially bumpy. As the size of the model grows, that plateau may get smoother and more difficult to deal with. Just a few comments about the nature of barren plateaus. They don't just exist. They usually emerge in the model training. They're not always nice and flat. They could be rough and bumpy. This is actually the worst case scenario because the first and second principal component they show the most variance in the data, and so if we look from different dimensions, we could have probably a more subtle and less bumpy view of that plateau. The presence of barren plateaus is often declared when facing difficulties in training, but such difficulties are not always linked to barren plateaus. The presence of barren plateaus does not mean the model is bad. It just means the model is difficult to train. And there are many well-known causes of barren plateaus described in literature, and there are many well-known countermeasures for those barren plateaus. Barren plateau strategy should not be applied as a default approach, as a precaution. That's because they could harm your model, they could make it worse. So we should apply them with some caution. When dealing with barren plateaus, we could focus on a number of different dimensions. We could focus on ansatz depth. We know that large ansatz, many qubits, many layers, many parameters, they invite barren plateaus. We could focus on cost function. And the global cost functions, which measures all qubits, they promote the emergence of barren plateaus. The local cost function measuring only a few selected qubits, they avoid barren plateaus. We could focus on the parameter initialization, and the previous studies showed that random initialization, most common in the development of quantum models, they encourage those barren plateaus. And we could look at the current practice in which people develop circuits as large as it is needed. They are randomly initialized because it's the simplest approach, and those circuits measure with the global cost function because that's often a default strategy in measuring the outcome of the execution of the circuit. We mix and match those focus areas, and we develop 4 groups of experiments: no strategy, shallow circuits with local cost, and 2 strategies of initializing the circuits, so-called the layer-wise learning and identity blocks. Our question is whether or not the barren plateau mitigation strategies could be detrimental to the model's capacity to learn. Can they harm the model? A good question: what exactly is capacity to learn? And that concept has many definitions in relation to classical models, especially neural networks, but we're interested in quantum models, and amongst many alternatives we selected 2 coming from the same team, Abbas and the IBM group of researchers. The global effective dimension, which combines the Vapnik and Chervonenkis the notion of effective dimension with the Fisher information matrix, and gives us the static probabilistic measure of the model complexity as the geometry of its entire parameter space. And that geometry can be derived from the gradients encoded in the Fisher information matrix. The local effective dimension, or LED, is a dynamic geometric measure of the model complexity in training, which is based on GED but affected by data distribution and optimization algorithm. So in our experimental work, each of the barren plateau methods was tested using a quantum neural network classifier. Each classifier had 10 instances, so we have some realistic statistics. And each instance was trained on Iris and Muniz data, and the reason for those data sets was because Abbas and colleagues, they use those 2 data sets, but also because they are very simple data sets which don't require very large models. The models which would perhaps develop barren plateaus, we were actually interested whether the barren plateau countermeasures could alter negatively, we had a negative impact on models which would otherwise train easily and well and nicely. In the process of developing and optimizing those models, we calculated global effective dimension and local effective dimension, and the results can be depicted in 3 dimensions, where the local effective dimension could be related to optimization iterations versus number of observations, or there are actually number of samples used to calculate Fisher information matrix. Since it's difficult to deal with 3-dimensional plots, we take some slices through the iterations, and also because we have very small data, very large data, we use log scale in the x-axis, and we catch the information from running all 10 instances for each classifier, so we could actually show the mean and the variance bands for each of those classifiers. Now, in the process, we were investigating local effective dimension as the model was evolving, starting from the point before training and then going through the entire evolution of the model. We had special interest in at the point of the peak testing accuracy and eventually at the point of finishing the training. We have a detailed discussion of those analytic results. Just a few points: that local effective dimension does evolve with training. It scales well with test scores, unless there is some volatility in the process, and that volatility could be like we observed with Iris data sets, which is small, and the optimization curves are quite jagged and random at points. The variance reduces with training, and global effective dimension was found to be a good predictor of what happens in a dynamic model at peak model test scores. So that was interesting, a few interesting observations. The insights overall were, the most critical insight was, with the exception of method 0, all tested countermeasures altered the model. The other insight was that LED is more influenced by the model structure and its optimization than the nature of data. We had data of a different kind. We have iris, simple numerical data, versus MNIST, which was images. When it comes to individual countermeasures, ignoring barren plateaus, our baseline approach had the best accuracy and the best local effective dimension. However, the prior work warned that such models are BP prone, so we recommend to use this approach with a great deal of caution. Models with shallow circuits and local costs, they converge quickly in training, and they reduce the large initial variance very quickly. The models, however, have not enough capacity to learn complex data, so they perform poorly. That was expected. The identity blocks parameter initialization had high accuracy scores, but the worst local effective dimensional tests. The authors of that method in the paper warned that the method is sensitive to the number and depth of identity blocks. We didn't play with those parameters in our experiments, so we found that method difficult to use to get good results. Delay-wise parameter initialization had the excellent accuracy scores and consistently high local effective dimension, but it was computation expensive. But that was the only approach to dealing with barren plateaus, which had good results, and it could avoid barren plateaus, and its performance wasn't worse than the method we should ignore, the baseline approach. So we compared 4 methods. We found that each of these methods had different impact on model training and its capacity to learn, and we used effective dimension as approach of understanding the capacity to learn. So thank you very much, and any questions?